right, let's get started. Okay, so there'll be an assignment coming out, probably come out tomorrow, something else to do today. It'll be due next week on Thursday and Friday, so it'll be a caddis problem to do, and let's do Friday, and then some regular problems to do on Thursday. All right, let's get started. Okay, so I just want to remind you about Piazza. So this is Piazza right here. So far we got 88 students have enrolled. So far there's been no action, but there presumably will be some action once there's an assignment. So be sure you sign up and get used to this, because this is our one conduit for communication. I know there are lots of email preferences you can set up, whether you want to be notified by email when something happens. You can customize all that. So please do that. Any questions or problems before we go on?
Are you going to go over the assignments or show us the assignments?
Okay, he's asking if I'm going to show you the assignments. No, they're not ready yet, and they'll just show up and you'll see them online. Okay, so today we're going to talk about complexity analysis. And I want to start with, we're talking about both experimental and analytical complexity analysis. But we'll start with experimental. So you've taken 2420 and you've done lots of experimental timing experiments to get at the complexity of things. How do you do that? If I ask you to time an algorithm, how do you do that? Who has some some guidelines for getting accurate timings? It's just like lab procedure. Yeah.
Run it a bunch of times and then average out the time.
Okay, you're saying run it a bunch of times and add up the times and average them?
Yeah.
Okay. Yes?
You should wait a little bit for the program to execute, like wait a second, so like the JIT goes and
okay, so for a variety of reasons, you I call it warming up the computer. You've got to run what you're going to run for a while before you time it. So the just-in-time compiler has time to run, and so the cache gets populated, the memory gets populated, and so forth. Yeah?
I remember we were taught to run like a for loop. That was empty right before we did all the really serious calculations of timing.
Okay, so he's saying run an empty for loop, again, that's related to warming up. Yeah?
Do some step-by-step analysis like you did yesterday, comparing the two algorithms.
All right, so if you're comparing two algorithms, yeah. What else? Yeah?
Increase the amount of time you spend on each time interval on a piece of data to see if it's larger amounts.
Okay, so to get results out, so it's not enough just to time an algorithm and say, okay, that took 10 milliseconds. You want to time it. Usually you have the data is a certain size. We'll call the size n. You want to time it. You want to time it for a certain size, and then you want to increase the size and time it again, and increase the size and time it again, so you can see how the time changes, how the running time is related to size. Because a single data point does you no good. And actually the number that you get out isn't that interesting either, because it will vary depending on what computer and programming language you're using. What you want is the curve. It shows you how timing scales with, how timing changes when as the problem scales. So if you time it, let's say you're doing a sorting algorithm and you figure out how long it takes to sort a 1,000 element array. How should you increase the size each time?
Double.
Okay, so you said double, and that's the right answer. Don't do like 1,000, 2,000, 3,000, unless there's an exception to that I'll talk about. But you want to do 1,000, 2,000, 4,000, 8,000, 16,000. You want to double because it just turns out, and I'll say more about it, that when you observe what happens as you double the size, you can tell the complexity of the algorithm just from that. At least the apparent complexity from the test you're doing. All right, so these are all good suggestions. So I've got some slides here, and it's going to mostly say what we've just said, but I just want to to go through this. Okay, so we said make your computer quiet. I don't know if we said that actually. Make your computer quiet means shut down extraneous processes. Make sure there's not some tab in your web browser hogging an entire core or something. Just get it as calm as possible. Then you want to warm up your code before taking data. So I say you want to run it for at least a second before pay attention to the results. But it's not enough just to run it. You got to run what you're going to be timing. Because modern languages, Java and C#, they do some compilation when you first run the program. So you want to make sure it gets a chance to do that. And here's something I find people don't pay attention to. Never time small intervals. Okay? So what that means is, let's say you have a quick operation. Like we're going to look at an example of timing how long it takes to do a binary search. So suppose you want to figure that out. You've got a binary search method. So what you do is you write a loop, and inside the loop you start the clock, make the call, stop the clock, record it. Do it again. So each time through the loop you're starting the clock, doing the operation, stopping the clock, figuring how long it took, adding them all up and averaging. You're violating the third rule there. You're timing a small interval of time because a single call to binary search doesn't take much time. What's a better way to do it? Yeah?
Time the whole loop and then time how long just the loop part takes.
Okay. So what she said is right. You time the entire loop. So you write a loop that runs 1,000,000 times maybe or whatever. I'll show you how to determine that as well. You time the whole loop. So you made that call 1,000,000 times. Then you time that interval and divide by 1,000,000. That's your average. Rather than adding up 1,000,000 small numbers and averaging. Now, it doesn't make a huge difference, but it does make a difference. Think about, I don't know if you ever had your pulse taken by hand, like they used to all the time in a doctor's office, but when they take your pulse, they don't say, measure, listen to one beat of your heart and then extrapolate. And they don't go, okay, that took that long, okay, that took that long, okay, that took that long, let's average. What do? They take 15 seconds or so and they count your beats and they average that. So I try not to measure any interval less than a second. I arrange so that my timing experiment takes about a second. Then I divide by the number of repetitions. What's the problem with that? Okay, he said overhead. When you time the loop, if you have a loop that's running a method that runs really quickly, you're timing not just the thing you want to time, you time the loop. So what I do is, after I time the whole loop with the method called in it, I time the loop with the method called not in it. Figure out how long a single repetition of the loop takes, then I subtract. Sometimes that timing overhead is significant, sometimes it's not. Okay? So that gives you a better result than timing a bunch of small intervals and adding them up. Yeah?
What do you do if, you don't know if your compiler is going to optimize or report it behind the scenes? It's going to do some unfolding, or maybe when you're just timing an nth loop, maybe your compiler will kind of skip over that and not really care about it.
Yeah, that's always a concern. Okay, so the question she's asking is, how do you know the compiler is not going to optimize the entire loop away because it sees that it does nothing? And that's a great question, and I'm always kind of paranoid about that the compiler is going to look at what I'm timing and say, oh, but nothing is done with the results, so let's just compile get that entire loop away. But in my experience, it seems that if you put timing code around it, it seems to not compile it away. So I don't think it's ever been an issue, at least in my experience. But it is something to worry about. And this is where I was just saying, account for timing overhead. And I'll show you an example, but I've already blabbed about that first point enough. And the second one is design, the last one is design and interpret your experiment carefully. So let's suppose you want to find out how long it takes how long a single call to binary search takes. How would you choose your data? You're trying to hit sort of the average case for binary search. You need an array, you need something to look up to time it. So how would you create the array? How would you pick the thing to look up? Yeah?
Make it totally random?
Okay, so you could, let's say you wanted a 1,000 element array, so you pick 1,000 random numbers. Sure. Put them, sort them. Okay? And then you have to look something up. How do you pick what to look up? If you want sort of average behavior, yeah.
Another random number and just do that over and over.
Okay, so you got to pick another random number. Each time through, pick a random number to look up. Well, what would be the problem with that? If you pick a random number, say you pick a random integer to look up in an array of 1,000 random integers, yeah.
Well, that integer might not exist. You can look up a random index.
Okay, so the problem is if you pick a random integer, it's unlikely to be in the array. And so what you're really timing in that case is the average time for an unsuccessful lookup using binary search, which is fine. If your goal is to, if that's your goal, if your goal is to get the average time for successful lookup, you need to, probably what you do is create that random array and then just look up every element in it over and over and time that. So you just need to be careful about picking your data that you're not testing some special case. At this point, let me just go to I'm going to show you an example program here. All right, so this is a program that does do the timing of binary search. And I'm just going to, it's written in C#. So what we've got here is, a couple of the versions use a fixed number of repetitions, so I'm using 1,000. In some of the other versions, I make sure I test for a minimum of 1,000 milliseconds, which is 1 second. This is a constant that's used. But basically, when the thing runs, it lets you pick between eight approaches. So I'm just going to take you through each approach and see what timing results we get. So the first approach times a single lookup using binary search. So it just times a single operation and shows that. So it doesn't warm up the computer, doesn't do anything. It just times an operation and reports it. So let's look at what time binary search looks like. Okay, so we construct a sorted array. So I didn't pick them at random. That really doesn't matter. I just sort the numbers from 1 up to the size, 0 up to the size. I create a stopwatch. I start it. I do the binary sort operation. I stop it, and then I report the answer. Okay, that's about as crude a measurement as you can make. So let me run it, and let's see. Okay, so we'll do operation 1. And that's going to be kind of hard to see. 0.18 seconds. Or, yeah, is that answer in? I can't remember if the answer's in milliseconds. It must be in milliseconds. Yeah, that's number of milliseconds that elapsed. Okay, so let me run it again. What do you think of that answer? That time 0.14. That seem long, short? Think it's accurate?
Seems pretty long.
Yeah, it seems like a lot of time, but who knows. So anyway, that's what you would get if you just took the most straightforward approach to testing. Okay, so let's look at version 2 here. So this is version 2. And what it does is it times, in this case, 1,000 repetitions and averages. So again, it constructs a sorted array, starts the stopwatch, then it does 1,000 operations. But what guidelines am I violating here? Yeah?
You're just timing a small.
I'm timing a bunch of small intervals and adding them up, and then later averaging. See, I average down there. What else? Yeah?
You're not taking out the loop overhead?
I'm not taking out the loop overhead. Well, actually, no. In this case, I'm not timing the loop.
Ah, yeah.
But I'm not warming up the computer, right? I'm just diagramming the timing. So last time we got 0.1 something. Let's see what happens with this. Version 2. Okay? That first measurement presumably was kind of off. Right? This is orders of magnitude smaller. Okay? And yet I have students that will hand in timing analyses and essentially do what I just did with version 1 there. It's just, it just doesn't work. Okay. So that's better. We timed a bunch of repetitions. Right? Let's look at this version here. Version 3 returns the time required to find the last element of array, operates by timing a loop that does it repetitions time, then calculates loop overhead and averages. So let's see what's going on here. I start the clock, I time the entire loop, and I stop it, and I figure out what an average repetition, how much time an average repetition took. Then I do it again, but notice I've commented out that thing right there. What she was worried about before, which I worry about too, is what happens if this entire loop is optimized away. But hopefully it won't be. So I compute the two averages, I display them just so you can see what they look like, and then I return the difference. Okay, so let's try that. So I don't remember what the answer was. So for 2 it was 3 zeros and then 1 9. And then we'll do it for 3 and see if that makes any difference. Okay? It actually looks slightly higher, which is unusual. But you can see that the thing is the average time was 0.0002. The overhead was tiny, and so really the overhead in this case made no difference. Yep.
What do you mean by overhead?
The time. Okay. So what I mean by overhead is right here. I am timing that entire loop. I'm only interested in timing that. But I'm also timing the time it takes to run the loop. So here, I time the entire loop with the method call. Down here, I just compile the loop, I time the loop without the method call and subtract.
Because that could, in theory, add extra time to what would be the search value.
Right, right.
Okay.
But a lot of times, especially if you're timing a sorting algorithm this way, the loop overhead's trivial. It's 3 decimal places or so below the time to sort. But it's something you can take account of. All right, let's try it again and see. Oops. Okay, so we'll do, I forget where I was. What was 2 was the sum of many timings. So that's not what I wanted to do. This is without subtracting the overhead, and this is with subtracting. And the problem is we don't get exactly consistent numbers. Oh, okay. I'm sorry, I'm confused myself. So I wanted to compare 2, sum of many timings with 3, with taking the overhead out. All right, now let's look at 4. We're gradually adding back in stuff. We're gradually obeying more of my guidelines. So this runs the loop for a second. So it won't time a short loop. It won't time a short interval. It times a long interval. Because even 1,000 repetitions of binary search are pretty quick. So what I do is I start the stopwatch, and then we'll have to stare at this a second to see what I'm doing. So I know how much, I have a variable that's going to keep track of the elapsed time, and that's how many repetitions I'm doing. So what I do is I enter the loop, I double the repetitions. So I multiply the 1 by 2, I get 2 repetitions. I start my clock, I run the loop for that many repetitions, I stop the clock, and I see how much time elapsed. Then, what's happening here? I just ran 2 calls to binary search, and I compare the elapsed time to duration. So what's the point of that? Yeah?
If the elapsed time hasn't reached the duration, how long you want the loop to run, then it's going to go through the loop again.
Right. So what he said was, I'm not going to count the timing until it's at least a second. And so I run the loop. It'll take a lot less than a second to run, so elapsed to be less than duration. Duration's 1,000 milliseconds. So I double the number of repetitions and try again. That'll take presumably twice as long. If that's still less than a second, I double it again. And I keep doubling until it takes at least a second. Then I use that measurement. Now, last night I was trying this. This laptop's just a few months old. And I took my code from last semester, and it broke. It wouldn't work. It was like infinite loop. Now, why would the code that worked last time I taught the class not work this time? Yes?
You might have used an int for the repetitions instead of a long?
Well, it turns out I was using a long for repetitions, but you're on the right track.
Hmm.
Right? I realized that it might take more than 32 bits worth of repetitions. But what I hadn't done was, this was an int. This index variable was an int. And so my new laptop was faster, and so that as I kept doubling I, it overflowed into negative territory. And it just didn't work. I had to go through and change all my ints to longs. So sometimes things can be confounding. All right, so what am I gaining by doing this? Besides, I'm saying you should only time long intervals of time. What else am I accomplishing? What other guideline am I now obeying? Yeah?
You're warming it up.
I'm warming up the computer on the exact thing that's being timed. Okay? So how much time will this loop run before it gets to a situation where I time it for a second, where the thing being timed takes 1 second?
At least a second.
Yeah, at least a second. Okay, let's see how that works. Let's say the first time takes a millisecond. The second time takes 2 milliseconds. The next one takes 4 milliseconds. The next one takes 8 milliseconds, and so on until we get up to 1,000 milliseconds. But if you add up the 1, the 2, the 4, the 8, the 16, 32, 64, 128, 256, 512 that didn't count, what's that add up to? 1,023. Okay? It turns out that this way, as long as it doesn't take a millisecond with 2 repetitions, so if you're timing something that's really, really long, it's a different answer. We're timing something that's pretty quick. So it runs for a second without using the results, and then it runs a second at the end and uses the result. So you warm it up for a second, then you time it for a second. And you don't have to guess how many repetitions to use. It just adjusts dynamically. So I do that, then I do the same thing, but without the binary search in the loop to get the overhead. I subtract, and that's my time. Okay? So this is version 4. So let's compare again. So we'll run version 3 for comparison. That's 0.00016 this time. And then we'll run version 4. And it's taking longer because it's dynamically, it'll take about 4 seconds. Okay? Okay, so we went from 0.00016 to something that's about 10 times smaller, 2.4 times 10 to the negative 5th. Another decimal, another 0.0 in front. Okay? Without much more effort. It's just this idea that it can dynamically figure out how many times to do the repetition. Okay? So this is sort of the key one, which is dealing with a lot of the objections I had. It's not timing a small interval, it's warming up the computer. It's accounting for loop overhead.
Should we try to warm up the computer for every method that we try to time, or just once for the whole?
Yeah, I think you should. The key is to run the code you're going to time for a while before you time it. Right? Because you want the exact code to have been run and gotten into cache and been compiled and all that. Yeah?
Wouldn't there be times though, like for example a binary search, like you might not be running it back to back to back to back, and like the first time you run a binary search probably would take longer because maybe a lot of the elements in the array are not in the cache yet on the processor.
Right. Okay, so he's saying it depends on what you're trying to time. If you're trying to find out just what's the complexity of this algorithm, then you want to get all those extraneous features that way. You don't want to. You want it to sort of be a pure measurement that doesn't depend on the cache, on things being in the cache or not. So you give it as big an advantage as possible. If you're trying to time how long it will take binary search on a particular computer when you first turn it on, then that's a different matter. But that's usually not what we care about. We want to get the curve. Yeah.
I was wondering, when you're calculating the overhead, would you actually have more repetitions, and would that be a little bit high because you're not having a binary search?
Okay, it is true that when we do this loop, where we do the binary search, there's going to be fewer repetitions to get to a second than when we do this loop that has nothing in it. There'll be more repetitions, but look what I'm doing. I'm computing an average time. So if I time over 1,000,000 repetitions and compute an average, and then the next loop I time over 1,000,000,000 repetitions and compute an average, I've still got an average. Yeah?
So is the goal here to measure how long it takes on a particular computer, or just to identify the complexity of the
Right. Okay, so he's asking, is the goal to figure out how long it takes on a particular computer, or to figure out the complexity of the algorithm? And it's the latter.
Okay, so in that case, would any of these eventually give you the right graph to identify that?
He's saying, wouldn't any of these eventually give you the right graph? The problem with not taking account for all these variables is that, okay, for example, if you do binary, suppose you didn't do any of this careful work, you just time binary search on a small array, and then you increase the array and kept timing. Well, the early measurements are going to be skewed compared to the later measurements, because the later measurements are benefiting from the computer warming up. So you want to, it's like doing an experiment in physics or chemistry or something. You want to control everything that you control, that you can control. Okay, any other questions?
Is there a mechanism to like throw out outliers, like when the operating system switches tasks, or anything like that?
Well, yeah, we can't control everything. There will be outliers sometimes because other things are going on in the computer, but we just do the best we can. Okay, here's number 5. This one, up here, what I was doing, let's actually look at what I was timing. I was always looking for the last element in the array. Down here, I want to find out the average time for, I want to do a little bit better. So what am I doing different in the loop here? I'm looking every element up once. So what I'm timing, each time through the main loop, I'm looking every element in the array up once. Okay? So that way I'm not, instead of timing the same lookup over and over again, I'm timing a bunch of successful lookups over and over again. And that'll give us a different value than looking up the last element. So that's sort of picking what you're timing a little more carefully. So if I do this, so again, just to remember, here's version 4. Let's remember, it was something times 10 to the negative 5th. So 2.5 times 10 to the negative 5th. And then we'll do version, wait, what version am I on here? 5. So that was, the previous one was looking up the last element, the time to look up the last element, and this is the time to look up an arbitrary element. And you get a different answer. We can puzzle about why that is. Okay, so number 6 just uses a different timer. So I was using a stopwatch. There's also something that tries to measure just the time spent on the process as opposed to clock time. So the stopwatch is clock time. This is supposed to be time on this process. So this is just 6. Look. Okay, where am I looking here? Let's try this again. So this is version 6. No, what I'm just wondering is why it's printing out a table here. Oh, I know what's happening. Let's go back up here to the top. The experiments 1, 2, 3, 4, 5 uses best practices. This one reports the average time required to a binary search for various sizes of arrays. 7 uses a different timer. I think I have it labeled wrong. So anyway, so this is, it's nice to be able to time algorithms, but this is what tells you the number you can use. So size 63 took 1.9 times 10 to the minus 5th. That's not what I care about. What I care about is how much it goes up by. So we went to a 127 element array, and now it's the difference between that and the previous time was 1.28 10 to the minus 5th. The next time the difference was 1.16 times 10 to the minus fifth. This one, 4.12 times 10 to the minus sixth. Now we're doing a longer array, 5.74 10 to the minus sixth. Okay, 4.94 10 to the minus sixth. And the next one, 4.67 times 10 to the minus sixth. So what are we seeing? We kept doubling the length of the array, and we looked at the time. The amount of time is sort of specific to my processor, but what we're seeing in the other column, where we're showing the difference between one time and the previous time. Yeah?
So it jumped up and then it kind of stayed the same. And
Okay, so initially, you know, it was, you often see this for small arrays when you first start. It's not very consistent, but then it settled down into what pattern?
It's not linear, bro.
What you saw was the difference, if the difference in time between a 500 element array and a 1,000 element array was the same, roughly, as the difference in time between a 1,000 element array and a 2,000 element array. So what is that characteristic of? If you double the size of the problem and the running time goes up by constant each time, that's a logarithmic curve. That's the point of timing. Okay? So I don't believe, this is on the web page, you can play with it if you want. We have the different timer there, and 8 gets into linear search. But I want to come back to this now. This is what I call doubling behavior. When you double the size of the problem, how do you expect the timing to change, the running time to change? So let's just go through this. Suppose you have an algorithm that runs in constant time. So it takes some amount of time for a given size, for n elements, and then you time it on 2 n elements. How long, what are we going to observe in the time? Right, it's going to be the same, it's constant, right? Right, so what I'm doing is I'm saying, okay, the difference, the time it takes for 2n minus the time it takes for n is going to be 0. So we're going to see the time stays the same. So if you do a timing experiment and you keep doubling the size of the input and it keeps staying the same, you're timing something that runs at constant time. Now, suppose the thing you're timing is a logarithmic algorithm like binary search, and you compare the time it takes, c times log of n. Let's say that's the function that gives you how long the algorithm runs. So for size n, it's going to be c times log n. For size 2n, it's going to be c times log 2n. What difference are we going to see each time it doubles?
Constant increase.
Okay, that's when we just saw a constant increase. So as a logarithmic function, as the input doubles, the output keeps going up by a constant. Okay, and we can show that. F of 2n minus f of n, the difference between f of 2n and f of n, so the difference between the value on n and the value on 2n, we just rewrote it. C times log 2n minus c log n. Where did this come from? Where did these two things come from? C log 2 plus c log n. It's just a rule of logarithms. The log of the product is the sum of the logs. So it's c log 2 plus c log n. And then you subtract, you get c times log of 2, which is what? Just a constant. Okay? C is an arbitrary constant. So that's all constant. So you get a constant difference. Increases by a constant. So if you double and you see a difference by a constant each time, you know you're looking at a logarithmic curve. What's going to look like when it's linear? Suppose you have a linear time algorithm, like linear search in an array. You double the size of the input, you double the running time. Let's see if we can prove that. This time I'm going to divide f of 2n by f of n. I get 2cn divided by cn, and I get 2.
why do you divide it this time?
Okay, I knew I would get that question. Why did I divide instead of subtract?
Because it's not logarithms.
Yeah?
I'm trying to use a ratio to compare the complexity.
Okay, but why did he said I'm using a ratio to determine the time complexity, but why did I use a ratio here and use a difference up above? Yeah?
Like, you already knew what it was going to be, but the purpose of this exercise is to prove it. So, like, wouldn't you just sort of guess and say, like, well, I think it's going to double, and then you divide it, and then see that, yes, it does double.
Right, so if we know it, what I don't want you to think is I'm cheating in some way. There's a pattern for each one. Sometimes the pattern, in the first two cases, the pattern occurs when you look at the difference between successive timings. Sometimes the pattern occurs when you look at the quotient. It just turns out that, suppose I had subtracted, what would I have gotten?
CN.
I would have gotten CN, which, how would you think about looking at the table and trying to figure out, did it differ each time by C times N? When you don't even know what C is, right? C is just some constant that depends on what computer you're running on. So it wouldn't be a very obvious pattern. But if you divide, you'll see this. So when you're looking at the data, you got to decide, okay, you usually know what you're expecting. So if you think you've got a constant or a logarithmic function, you'll look at the differences, the deltas. If you're thinking it's like something else, you'll look at the quotients. Yeah?
When you say it just increases by n times, which is when you
It increases by n times.
yeah, so when you increase it by n, it increases by n times. So
Well, it increases by C times n times.
yeah, some constant.
But you don't know the constant. It's easier just to look at the quotient. Yeah?
So when you say if the difference is Cn, you could say that it's also twice as much as your original. Because if you
Yeah. The bottom line is, if you subtract, you're going to be looking for a difference of C times N, and you don't know what C is. If you divide, you're just looking for 2. That's easy to recognize. It's easier to see that something is, the quotient is 2 each time than it is to say the difference is C times some arbitrary constant times N. It's just easier to observe. You can try it both ways, but this is how you recognize. Sometimes you recognize it by looking at the difference, sometimes by the quotient. What would you see if it's an n log n algorithm?
It'd be double, but just a double.
Right. So n log n isn't much worse than log n, than n, rather. So what you'll see is it will a little bit more than double. So if you do the math, f of 2n divided by f of n, so there I set it up. We get basically the cn's divide away, and we get this. Then we use that log to turn it into 2 log 2 plus 2 log n. We divide, we get 2 log 2 divided by log n plus 2. Okay? Because this one comes from dividing this by log n, and this comes from dividing 2 log n by log n. So there's your 2 plus this thing right here. So what can you say about that thing right there?
It's some constant.
Well, what is 2 log 2 is a small number. Log n is an increasing function. So what would you see in practice? I say it doubles plus a little bit more. What happens to that little bit more as n gets bigger?
Increases very slowly.
That decreases. Okay? The bigger n is, the smaller this is, right? Because as n increases, the denominator gets bigger. And so this gets smaller. So you're looking at a logarithmic, n log n algorithm. It will be a little more than doubling, but it will gradually settle down to where it pretty much looks like doubling. It's hard to tell a difference with timing experiments between n and n log n. Okay? What about quadratic? If you double the size of the problem, what happens to the running time?
Quadruples.
It quadruples. Well, let's see why. Let's divide f of 2 by f of n. We get c times, we plug in 2n, we get 2n squared, divided by cn squared. It just reduces to 4. So if you see it quadrupling each time, okay, that sounds like an n squared algorithm. What about cubic? Is that a word? Octuples?
Mm-hmm.
We do the division, it's 8. So, yeah, about that. Then exponential. All right, here's the thing about exponential. If you time an exponential algorithm by doubling the size of the input every time, yeah, it takes, you won't do that very long before it takes forever. Okay? So if your running time is 2 to the n, what happens when you increase n by 1? It doubles. So if you suspect you're timing an an exponential algorithm, don't double the size of the input each time, increase it by 1. And when you get that, so bottom line is you're dividing f of 2 to the n plus 1 by 2 to the n and you get 2. So if you increase the problem size by 1, the running time will double. If you double the size of the problem, running time will square. Assuming I've left out a leading constant here. It's a little more complicated than a leading constant. But for exponential algorithms, just want to increase by 1 each time to see what happens. So it squares or it doubles for n plus 1. Okay? So my message here is that you can look at the curve. You can just actually look at the deltas or the quotients, and you can a lot of times just read off the complexity of the algorithm.
What about factorial that we ran the last time?
Yeah, well, what would happen when you increase, if the running time is n factorial and you increase n by 1? What's the quotient going to be?
Multiplied by n plus 1.
Multiplied by n plus 1. So the reason that's worse than exponential is, at least this way, every time you increase by 1, it goes up by the same factor of 2. Whereas with n factorial, it goes up by, the first time is, when you go from 2 to 3, factor of 3, then a factor of 4, then a factor of 5. The factor keeps getting bigger. So
what happens when you double? It's more than
when you double, I don't know what happens when you double. It's bad news. So.
Well, how about asymptotic?
Well, we'll worry about that offline. Yeah.
Are there any other categories we should be aware of?
Well, these are the ones that occur in practice. We'll probably see an algorithm that's like n squared log n.
Okay.
But yeah, I mean, there are an infinite number of categories, but most of them don't have names. Yeah?
I'm just curious, will we ever get to n raised to the n?
But that's factorial.
Yeah. Yeah, n to the n is, yeah, I don't think we'll see that either.
Oh, we just put that.
Okay? Okay, so that's my doubling behavior. Now I want to go right back to my program here, and I want to run it. Oh wait, this is Eclipse, something else. Okay, this time I do experiment 8, which times linear search. So what should we expect? It's going to print out a table of timings and then a table of ratios of successive timings. What are we going to see? What will happen each time the size of the array doubles? What happened to the running time? Linear search, yeah.
It increased by a constant.
No,
Search.
that's binary search. Linear search, it should double. So that's version 8. So first data point comes out. You can't tell anything yet because that's a raw timing. What matters is the ratio. So we're at 3 times 10 to the minus fifth. Okay, the first ratio was 2.39. The next ratio, I've doubled the array size. It's 1.92. Then we're at 1.96. We're at 2. Okay? So if I were just printing out rounding to 1 digit, it would have been 2 pretty much all the way down, I think. But you see this pattern. We could let it run for a while longer. You're going to see 2s. Now, sometimes you get to a point, I'm not sure exactly why this happens, but the array gets so big, I've had it actually be faster for binary search anyway. It was faster for an array twice as long as one that's not twice, that's half as big. I'm not sure why that happens. If anyone could tell me, I would like to know. I think it has something to do with the cache or the memory or something. In fact, this might be a spot where a little anomaly happened. So this is pretty good evidence that what you're timing is a logarithmic function.
You mean linear?
A linear, sorry, thank you. It's doubly important that you correct me because I'm being recorded. So no longer can I deny I said something. Okay, so that's experimental complexity analysis. We won't be doing a lot of that, but this notion of doubling behavior is important to me, so I wanted to talk about that. Yes?
Just for clarity, because it was showing by a constant each time, so doesn't that imply that it's a logarithmic?
It wasn't, what I was displaying in the ratio column, in the third column was ratio.
The ratio, oh,
Yeah.
okay.
Yeah, we got to be clear whether we're talking about ratios or deltas. If I'd done deltas, in fact, let's try it and see what it looks like. So if I come down here to do this, and oh, it would be up here where I'm doing deltas. Okay, here's approach 8. I keep doubling. I'm dividing. I'm doing current time minus previous divided by. So this time we'll do the difference instead of the quotient and see what it looks like.
Still going to say ratio.
It'll still say ratio, but it is a delta. All right. So the raw times should be similar. So the first delta is 4.32 10 to the minus 5th. I think what you're seeing there is what's happening to the deltas.
It's doubling.
The deltas are doubling each time. But it's more in your face if you just see a 2 each time. Okay? Any other questions? You gotta do this back. All right, let's take I'll take that question and then we'll take a break. Yeah?
I don't know if I'm jumping ahead, but how do we exactly calculate the complexity in terms of steps?
You're jumping in.
Okay.
So let's take a break and we'll talk about that. Okay, let's get started again. Okay, so now we're going to move to a different set of slides, talk about asymptotic complexity, which we'll do much more of than experimentally. So it's nice to be able to quickly figure out for yourself the complexity, the running time complexity of an algorithm without having to do an elaborate timing experiment. And that's what asymptotic complexity is about. It's about analyzing the algorithm without running it, looking at the algorithm and figuring out what its running time is. And it's a lot harder, it's a harder thing to learn to do than doing timings. But in the end, it can be a lot faster. So just to remind you how to do that sort of thing, let's analyze selection sort. And so there's the code for selection sort. And it's just 2 nested loops. You remember what selection sort does is it searches the entire array for the smallest element, and then it swaps the smallest element with whatever's at index 0. Swaps them. Then what's it do? Now element 0 is in the right spot, so now it goes from index 1 to the end looking for the smallest element in that interval and swaps it to index 1. So it's basically for every element up there, the outer loop is looking at every index, and the inner loop is looking at increasingly smaller intervals looking for the smallest element, and then it does a swap. So if you want to analyze this, once you're experienced, you sort of look at this and say, oh, that's n squared. But let's break it down and be very systematic about it. What do we need to do if we want to figure out, sort of predict the running time of this algorithm as a function of n? Yeah?
To look at the size of the list, determine how many times you have to iterate the list.
Okay, so the size of that array there, data array, is crucial. So we'll call that n. Okay? So what do we do with it? What do we do with n? We're going to count. What are we counting? Yeah?
The number of times you look at each.
Okay. So we could count the number of times we look at each element, the number of times we compare elements. Basically, we need to count everything. We want to count all the operations that are performed. So I broke it down and I figured out these are the operations that are performed. It does that assignment there, int I equals 0. It does comparisons. It does increments. It does that. It does this, and so on. I don't know if there are probably small things I've left out, but that's pretty much it. So fundamentally, when you're doing asymptotic complexity analysis, you are counting operations. So let's count them. How many times do we do int I equals 0? Over the life of the entire program, we only do that once. How many times do we do that I is less than data.length thing?
And
okay, we do that once per element.
plus 1.
Plus 1, because there's n successful comparisons, and then the loop ends when there's an unsuccessful comparison. Yeah?
Yeah, that's supposed to be I less than data.length and I plus plus. Or am I reading that? There's no I's in the operation part.
Look, so this I is less than data.length is this thing right here.
Oh, okay, I'm sorry, I was looking at the wrong column.
Yeah. Okay. How many times do we do the I plus plus?
N times.
Okay, we increment it n times. Okay? And, n plus 1, in the end, it doesn't matter, but I'm just trying to be as careful as possible. How many times do we do int smallest equals I?
And
Each time through the loop. So the outer loop, so that'll be n times. How many times do we do int j equals I plus 1?
and
N times. J less than data.length. Okay? Now where did that come from?
The smallest to like the largest.
Right, the first time we enter that loop, that inner loop, it runs a number of times, right? The inner loop is run n times. The first time it runs, it's looking through the entire array for the smallest element. So we do that comparison n times. The next time, it only has n minus 1 elements to look at. The next time, n minus 2, n minus 3, n minus 4 down to 1. So it's the sum of those things, 1 plus 2 plus 3. That's how many times we do that single comparison.
So can you use Gauss's rule?
Yeah, we'll simplify it in a second, but right now we'll just write it as a summation. Yeah?
would the last one be n plus 1? Maybe?
I'm pretty confident it's n.
Okay.
I've been staring at the slide for a few years, and I think I can do that.
Well, isn't it?
I don't want to do it. It very well could be n minus 1 n or n plus 1, but I think it's n.
Well, the first time it's you know, search through.
Yeah, it's really not very instructive to spend 5 minutes trying to figure out exactly if I'm wrong, because I don't think I am. But you can tell me after class if I am. Okay, that j plus plus. That's how I think that works out. Turns out we do that comparison that many times. We do that. We do n swaps. The way I've got the loop written. Okay. So we carefully count how many times we do each operation. Now, if we want to predict the running time, what do we do?
Sum them all up.
Okay, he said sum them all up. That won't quite work, though, will it? What if I want to predict how long this thing would take on my computer? Would it work to add them all up and say it'll take that many milliseconds?
No, you need to know how long each operation will
Right. So what we'd have to do now is time each operation. How long does it take to do int I equals 0 on my computer? How long does it take to do I less than data.length? And multiply by those times, and then add them all up. Well, that's a hassle. So we'll look at it. We don't actually have to do that. But let's start by simplifying the table. We need to do something with those summations. Okay? So there's your rule. The sum of the first k integers is k times k plus 1 over 2. I know you've heard that before. Commit it to memory. Okay? K times, if you're adding up the number of integers from 1 to 100, it's 100 times the next integer, which is 101, divided by 2. Okay? You can prove it via induction. You've probably seen that as well. I'm not interested in proving it. I just want you to know it. So what's the sum of the first n integers?
n times n plus 1.
No, just just use a different variable, n times n plus 1 over 2. Now, you know that one rule, and it turns out you can deal with all kinds of summations now. So for example, I want the sum of the first n minus 1 integers. Okay, so now it's n minus 1 times the next integer, which is n, divided by 2. Right? So it's n minus 1 times n divided by 2. So it's always the last integer in the sequence, if you're summing all the integers, times the one after it divided by 2. What do we do here? We're adding up the even integers from 2, 4, 6 up to 2n. There's still n elements in the sequence, but they're not one after the other. Yes?
Factor out of 2.
Factor out of 2. That's 2 times that summation, and we know what that is. Right? So it ends up being 2 times n times n plus 1 over 2, which is just n times n plus 1. Now we're adding up odd ones. Nothing, we can't really factor out a 2. So the general rule is, if you don't know how to sum a sequence like that, try converting it to one you do know how to sum. So this is similar to that, right? What's it take to turn this sequence into that one? Add 1 to each element. How much total are we adding then?
Minus 1.
We're adding 1 to each element. They're n elements, so we're adding n. So we simplify it. We turn this into 2 plus 4 plus 6, all over 2n. Then we got to subtract away the n that we added into here. Now we're in business. We know how to sum that one, so it's just n times n plus 1 minus n, which would also be
N squared.
n squared, but I don't think I went the extra step. So that'd be, you simplify that to n squared. Now this doesn't work for like your geometric sequences. We'll look at a different rule for that. We're doubling each time. But if you're summing integers where there's a constant difference between the integers, your goal is to simplify to something you know how to do, and you always know how to do something. You just know that rule. Okay? So back to here. Now we can simplify the counts. So that, look in the right column, that first summation is that, and then that, and then that, and then that. All right, now we've got to somehow figure how much time that'll take. So what we're going to do, so see what I replace the operation with, they all take some amount of time. So I'm just going to say, the first operation takes a milliseconds, or I don't know what my units are going to be, it doesn't matter, and on through j. I multiply and sum, and that's it. That's not very illuminating, but that's what you get if you do all that. Yeah?
Just a little confused. How come the first couple were just n, but the second 4 are summations?
Okay, let's go back here. Why do we end up with summations in the right column? Where do these 4 summations come from? Why do we have summations showing up in other places we don't?
The bounds are changing on the loop.
It says the bounds are changing on the loop. That's why the summations telescope, 1 through n. The bottom line is the outer loop runs once. The inner loop runs n times. And each time it runs for a different amount of time. So the first time it runs basically n iterations. Next time through the outer loop, the inner loop runs n minus 1 repetitions and so on. So that's why we get the summation. That's like the first time the inner loop runs, the second time the inner loop runs, and so on down to the last time the inner loop runs. That's how many times it does that comparison. All right, back here. Add it all up, collect terms. So you've got something times n squared plus something times n plus something. But what can you say about all these things we're adding up here? That's just a constant. These are all constants. 2 is a constant. So same thing right here. So we'll just simplify that. Okay? So there's some constant times n squared plus some constant times n plus some constant. That's going to be the running time of selection sort as a function of n, and the constants depend on what computer you're running it on. Okay? Now, normally what you do is you don't do such a laborious analysis. You just look and say, okay, I've got a nested loop that depends on n. I got an outer loop that depends on n, inner loop that depends on n. We're adding 1 each time. So nested loops like that are n squared. You get used to it. But this is where that shortcut comes from. So it's looking to me now, to analyze an algorithm, we need to count the operations, time the operations, and come up with a formula. But we just care about the doubling behavior. Right? If we can just figure out the doubling behavior of this function right here, we don't need to know the constants. We just need to know those R constants. So if all we care about doubling behavior, the constants don't matter. They'll sort of divide out. So we can throw them away. So we can say the running time grows at the, roughly at the rate that does. And furthermore, if all you care about is doubling behavior, the low order terms don't matter. Now how can I say that? How can I say that to do the doubling behavior, we do the n squared plus n plus 1, we just throw away the n plus 1 part? Yeah?
For huge n squared is going to be orders of magnitude larger than n.
Right. It's called asymptotic complexity analysis because we're interested in what happens as n gets big, as it approaches infinity. And n squared plus n plus 1, the low order terms get smaller and smaller and become insignificant. So when you do the quotient, you get if you divided n squared plus n plus 1 by 2n squared plus 2n plus 1, or the other way around. We divided 2n squared plus n plus 1 by n squared plus n. All right. I can do better than that. Not working either. This is left over from another class. Okay. So this is f of n. What's f of 2n?
4n squared plus 2n plus 1.
Right, so f of 2n is 2n squared, which would be 4n squared, plus 2n plus 1. If we want the doubling behavior, we divide. So what are we going to get by that? What's the quotient? Well, it's going to be 4n squared over n squared plus n plus 1 plus 2n over n squared plus n plus 1 plus 1 over n squared plus n plus 1. Okay? And we keep doing this. We're going to get let's see, divide through by n squared, we're going to get 4 over 1 over, by the top divided by n squared, we get 4 over 1 plus, well, I'm not helping my calls here.
Plus 1 over n squared.
Okay. Yeah, that works. Okay? So and this becomes, if I divide through by n, I get 2 over n plus 1 plus 1 over n. And over here, I've got the same thing, 1 over n squared plus n plus 1. What happens as n gets big?
Can you just apply the Hopital's rule?
Becomes 4.
Yeah, in the limit that becomes 4. Right? As n gets big, that goes to 0, right? So the denominator becomes 1, and you got the 4. What happens as n gets big here?
The whole term goes to 0.
That whole term goes to 0. I mean, it goes to infinity rather, and the denominator goes to infinity, and the whole thing goes to 0. Same thing here. So basically, the answer is 4.
So you got to take the Hopital's rule, or?
Well, it will. Okay. So the the key thing is we would have gotten the same answer if we had just simplified this and said, you know, instead of saying f of 2n was 4n squared plus 2n plus 1, we just simplified it to 4n squared and ignored the low order terms. And same thing here. Ignore the low order terms. Do the division, you get 4. So the nice thing about this analysis is you can ignore the constants, you can ignore the low order terms. All that matters is the high order term. And that's the key thing in complexity analysis. Figure out the high order term. Right? You don't have to work all as hard as we did there. So back to this. All right, so I'm just summarizing there what I said. Now, let's think about this. When I say that selection sort is O of n squared, what am I saying? What does that mean? I say selection sort on an array of length n is O of n squared. What am I claiming?
Isn't that saying like in the worst case scenario?
Okay, so he's saying in the worst case scenario?
Selection sort doesn't.
That's not what it's saying. Yes?
Are you saying that's what a curve looks like?
Well, informally speaking,
Yeah.
that's one shortcut we'll take. That you're saying something about what the curve looks like or what the doubling behavior is. Okay? Yes?
The up or down can be modeled by an equation that follows the set.
Okay. That's the key. O of n squared, big O gives upper bound on something. Now, you often use it to give the upper bound on the worst case. But you could also put an upper bound on the average case and upper bound on the lower case, on the best case. Okay? Big O is upper bound, not worst case necessarily.
So how about big omega?
We'll talk about that, yeah. So when I say a function f of n is O of n squared, there are two ways to look at it. We can sort of get this informal notion, intuition I want you to have, and we could also get really formal about it. We can do both. But let's start with the informal. When we say a function f of n is O of n squared, we are saying its high order term is no bigger than an n squared term. So when I say selection sort is O of n squared, I'm saying that, well, let's say I'm saying the worst case of selection sort is O of n squared. Then I'm just saying that if you figure out the worst case, and the way we just did, very carefully, the high order term will be n squared or smaller. That's what it's saying. So, is it true to say that selection sort is O of n cubed? What do you think? Is that a true statement? The worst case of selection sort is O of n cubed.
Yes.
Yes.
By this definition.
That's an upper bound. The higher order term is no bigger than n cubed. That's a true statement, right?
So in this case, would we want the least upper bound?
Well, yeah. Usually, you're saying more by saying selection sort is O of n squared is a stronger statement than saying it's O of n cubed. They're both true, but you prefer the lowest bound possible. Okay? Selection sort is O of 2 to the n even. Because the higher order term is no bigger than 2 to the n. Okay? You're also saying that in the limit, so as n gets big, you're saying that f of 2n is no more than 4 times f of n. Or f of n's rate of growth is less than or equal to n squared's rate of growth. So when you say something is big O of some function, you're saying that if g is big O of n squared, g of n is big O of n squared, we're saying that n squared grows at least as fast as g does. Okay? So you put an upper bound on the rate of growth. N squared's rate of growth is an upper bound on f of n's rate of growth. We're not talking about actual values. We're talking about how the doubling behavior essentially. Now, do you talk about omega anywhere before this class?
Yeah, 2420.
Okay? So omega, what's it for?
Lower bound.
It gives a lower bound on the rate of growth. Okay? And we can use all the same stuff. In this case, we're saying its higher order term is no smaller than an n squared term, and all these things. So big O bounds from above, big omega bounds from below. Okay? What about theta of n squared?
Oh.
See, now we're in business. Theta of n squared is saying, if you say something is theta of n squared, you're saying it is both O of n squared and omega of n squared. In other words, it is quadratic. Okay? That's the strong statement. Now, in a lot of books and in a lot of informal conversation, people often say O when they mean theta.
Yeah.
You know, they say best case of quicksort's O of n log n. Well, that's true, but it's better to say theta of n log n. We really know it's no bigger, no smaller. It is n log n. So in here, it's going to be the higher order term is an n squared term. It grows as the doubling behavior is a factor of 4. The rate of growth is the same as n squared, and that. Yeah.
I'm a little confused here. Are each of these letters describing the average case, worst case, and best case, or
okay?
Confused for each?
So he's saying, do these apply to the average case, the worst case, or the best case? Depends on what you're claiming. They're just a way of putting bounds on functions. So you can say, okay, the worst case for selection sort, that's a function of n. So you can put a bound on it. Say the worst case is omega is omega of 1. Okay, that's a true statement. That's a lower bound. Or you can say the average case of selection sort is this, or the worst case. It just depends what you say before you give the bound. Yeah.
So I guess I'm a little bit confused because just going off of 2420 and what I learned there. So with the equation that we did with selection sort n squared plus n plus 1, just asymptotically we determined is basically just
n squared.
behavior is 4, right?
Yeah.
So right there though you're saying big O of n squared, that is the upper bound. So wouldn't we say that it's omega of n squared, that selection sort algorithm, because that has to at least be n squared?
The strongest thing you can say is that selection sort is theta of n squared. Because it never takes more than n squared steps. You know, an O of n squared steps, it never takes less than an omega of n squared steps. If the upper bound and the lower bound are the same, then you can use theta.
But wouldn't we say in this case omega, because there is that n plus 1 there that we're not really taking into account?
No, we're not putting bounds on the values of the function. We're putting bounds on the asymptotic rate of growth.
Okay.
So any function that has an n squared as the lead term, as the high order term, no matter what the low order terms are, as n gets bigger, they all look the same. You double n, you quadruple the function. Right? It'll eventually settle down into that behavior. So let's just do, in the few minutes we have left, let's do this. There's your function, 3n squared plus 5n plus 3. What's true? Is it, well, I'm saying what is true. If you have any questions, you can ask. It's O of n cubed. So the way I usually think about it is I just think about it in terms of we're making assertions about the higher order term. So the higher order term is n squared. Take away the constant, take out the lower order terms. N squared is O of n cubed. It's no bigger than n cubed. It's no bigger than n squared log n. It's no bigger than n squared. Why is n squared not O of n log n? Because n squared is bigger than n log n. Same thing here. Let's say these are all true statements. N squared is omega of 1, omega of n log n, omega of n squared. Because all those things are less than or equal to the n squared. The rate of growth is. This isn't true because these terms are bigger. These terms here grow faster than this does. Okay? And I guess it seems to have come out of order. I threw in some notation to have it defined. Little o, little omega.
But that's just like less than.
Yeah, well, I'll just end with this. We'll begin with this slide next time as well. But I just want to show you here. Basically, there's notation. There is little o, big O, theta, big omega, little omega. They correspond to assertions about the rate of growth, less than, or equal to, greater than, greater than. They're just ways of putting bounds on the rate of growth. We will continue this next time.